more specifically about the hydrodynamics. So, well, unfortunately, I don't have much new really, because the stuff I'm going to show was primarily done between approximately 2014 and 19 with the help of my students who are all listed here. Two of them I have already, well, actually all three of them have graduated. Linian was the last, his defense was exactly last week on Friday, it's exactly that time. So I'm going to talk about the classical liquid metal battery, which I suppose I don't have to explain since that's the seminar on this topic. So we consider the three-layer system, liquid system, consisting of a light metal at the top, heavy metalloid of that type at the bottom, and the layer of the molten salt electrolyte in the middle. And the property of the molten salt electrolyte that it allows the positive ions of the light metal to go through it, but not anything else. So these three liquids are perfectly immiscible, or we assume them to be immiscible. And depending on whether you do charging or discharging, this positive ions of light metal A, they travel through the electrolyte. Then you do charging, they travel to the upper layer from the low one, and so forming a large amount of pure metal A at the top and pure metal B at the bottom. Then you are discharging, they are traveling back and forming a compound, an alloy with the light metal B. And the energy saved is, of course, the difference in the internal energy of light metal A being in the pure state and in the state of being alloyed with B, which is shown in this slide, which I will just skip because it's not really what we are going to talk about. What's important for us, though, that if this battery ever exists, the current traveling through it, electric current traveling through it, is going to be large during charging and discharging, of the order of 1 ampere per square centimeter. That's it. What is written here is totally wrong. It's 10,000 ampere per square meter, or 1 ampere per square centimeter. So, and then of course the history, which is listed here, which I will skip because everybody knows it, and the advantages, which also you can read in the literature. I think the main disadvantage that, as far as I know, the working system in its originally designed shape, I don't know, it probably doesn't exist yet. But this is a theme from an excellent review which was published in 2018, which I do strongly advise to students present in this seminar to read if you are interested in the topic, which is here. So that's the same system, but a more technically detailed view. And that's another version of the system in which light metal is contained in a metal foam and immersed into the electrolyte. So in this case, the light metal, of course, cannot flow, not much anyway, but otherwise the scheme is very similar. So going back to what I'm going to show, I'm going to consider an idealized liquid metal battery of the originally kind of imagined type. So a free liquid layer, metal B at the bottom, metal A at the top, electrolyte in the middle. There is going to be walls, which we will assume to be electrically insulated on the side, and just the perfectly conducting current collectors at the top and bottom. We will consider either cylindrical or cuboid shapes, and we will focus on hydrodynamics, on electromagnetohydrodynamics of this, system. And if you do that, we have to consider several critical facts, such as the huge, well, not huge, well, quite significant stratification in terms of the density. This metal B is heavier than electrolyte, and the electrolyte is heavier than the light metal A. So this system is stably stratified. The huge difference exists between the electric conductivity sigma. It's for metals, it's about of the same order of magnitude, more or less, very high, maybe at the level 10 to 6 or so. For the electrolyte, it's much lower, about 4 orders of magnitude lower. And if we talk about electric conductivities, then we see that the thermal conductivities of the metal A and metal B are also pretty high and about the same, while the thermal conductivity of the electrolyte is low. And here is the current now properly shown. And as you may surmise, or you may read in the literature, including this 2018 review, which I mentioned in one of the slides before, the system, if you look at it, well, it does present some very serious technological challenges. Of course, it must be hot. It has some issues, multiple issues. It's not as simple as it may look, but also it is a very, very enticing system for fluid dynamics research, because it has, well, not all, but quite a large number of the thermodynamic, of hydrodynamic effects in it. And they all exist together and they interact with each other, and we don't really always know which one is important and which is not. And all that happens in the presence of electromagnetic fields and so magnetohydrodynamic effects. I'm going to show what was done in our group over these few years from, as I said, approximately 2014 to 2019. And there will be 3 topics. One of them is thermal convection. And here I would like to say, if anybody wants to ask anything as we go, then please feel free, just raise your voice. Otherwise, I will not see you or hear you. Okay, so the first topic is the thermal convection, and this is evident that it's going to happen because we have, we have a layer here of electrolyte which has a rather low thermal conductivity, low electric conductivity, so it's quite resistive, and you pass very serious electric current through it, so there must be Joule heating, just the internal heating by this passing currents. And we are looking into this effect. We just assume, we just look at the thermal convection. We ignore anything else. We can see the cylindrical cell of aspect ratio 1. Take the thermally insulated side walls, top and bottom walls I assume to be some kind of metal plates maintained at some constant temperature. We ignore the movement of the liquid-liquid interfaces for now. We take physical properties of some typical electrolyte at typical temperature. We take the typical strength of electric current, and we calculate what the internal heating rate must be in this case. And if you're interested in details, then these are in this paper. And I will be happy to provide the file if anybody is interested. So what do we have? We have 3 layers, metal, electrolyte in the middle. The electrolyte is exaggerated in thickness here, of course. And so you do have a little bit of heating in the metals, but it's totally insignificant in comparison to the heating you get in the electrolyte, simply because the electric conductivity is so much higher. And the electrolyte, you have the uniform internal heating. And if you just solve the conduction, the heat conduction problem, one dimensional along this vertical coordinate z, then you will get this profile of temperature that would exist if there are no flow of liquids in the system. So easy. And of course, we see now, all right, the temperature goes like this. It means that from the middle to the top of the electrolyte, in this zone here, we have a rather strong, unstable stratification. Yes, the temperature decreases from hot to cold here. So that's where the natural convection must occur. And so we try to treat that numerically. We solve the standard Bussinesque system for incompressible fluid, except then we include the buoyancy term is here. Right, this is all in non-dimensional form. The temperature is counted as deviations from the average, which, well, from some base, which we take as the temperature of the walls, top and bottom. We do include full electromagnetic effects in the quasi-static approximation typical for the liquid metals. So we assume that the current is given by the Ohm's law here. The potential, the electric potential phi is found as the solution of a Poisson equation expressing instantaneous electric neutrality of the liquid. And then we calculate the Lorentz force and put it in here. That's it. So this is the magnetic field which is imposed and which in principle has two components. One component is the azimuthal magnetic field that goes around the cell, which is generated by the current that flow through the system by the vertical current. And there is also, let's call it three-dimensional component, which comes from the outside, from the supply lines, from the neighboring cells and so on. So the non-dimensional parameters are the Hartmann number, which we take as a measure of the strength of the MHD effect, and the Grasov number, which is the strength of the thermal convection. The Prandtl number is fixed, of course, and the Reynolds number is, in this case, it's just the square root of the Grasov. So it's important to look at this. We are using the radius of this cylindrical cell. It must be R2 here and here. We use the radius of the cylindrical cell as the length scale. This is a bit awkward because the convection happens in this area primarily. Then they, of course, will penetrate all over the cell. But in this view, the appropriate length scale is the thickness, the half thickness of the electrolyte layer. Since we are going to vary it, so we will just take it as an additional parameter, and we do still use this uniquely defined R as the length scale here. So that's the thing to remember. So the problem is solved numerically. The solver has been with us for more than 12 years now. It has been continuously updated, improved, expanded. The literature here, that's the papers, just a few papers where the same solver was applied before this work was done. It's the second order, very conservative, finite difference solver on a non-uniform grid, effective and accurate for the situations, and we have electromagnetic effects, MHD effects, sorry, and thermal convection and strong shear and thin boundary layer, all these things. So we have the same shape of the cell, but we have three different thicknesses of the electrolyte. And of course, if our Grasov number or the heating rate, if you want, is sufficiently high, then we do have the natural convection, thermal convection instability, which is illustrated here. We just start with a pure conduction temperature distribution, add some noise low amplitude noise, and just let it run. So we don't really do the eigenvalue analysis or anything. Just follow the weak perturbations and see if they grow or not. In this case, they do, of course, grow, is shown by the kinetic energy of the flow, by the square deviation of temperature, and this is the growth rate. This line, which is on the right axis, that's just the growth rate. So we even have some period where you may say it's more or less exponential growth, and then it of course saturates at some level, so the growth stops. So this is one case. Now we varied the Grasov number, the thickness of the electrolyte here, and we saw where this instability first occurs, and so we found the critical Grasov numbers. And if we recalculate these Grasov numbers to the thickness of the electrolyte, we get these numbers here. And if we recalculate them into the Rayleigh number based on the half of the electrolyte width, then we get these values here. And then if we take the, yes, for every such h, if we take the radius for every such non-dimensional thickness of the electrolyte, if you find what the radius of the cell should be at this electric current, at these materials for the thermal convection to start, and we see that it's really, really small. So unless your cell is less than a centimeter, more or less, you are going to have the thermal convection caused by Joule heating of the electrolyte. Now, for comparison, there are data, classical data, experimental, I think, for internally heated layer, just a single layer, uniformly internally heated, and the critical Rayleigh number is about 560, which can be compared to what we see here. So now, how does it look? It looks like this. This is an example of an unstable flow. Then the electrolyte layer is 1/10 of the total height of the cell. This is a temperature field in the vertical cross section, and these are the free horizontal cross section through the middle here, through the bottom layer and through the top layer. On this free, we see the vertical velocity. So some kind of a typical convection pattern at a not very large Grasov number. We have the, it's a chaotic motion. I wouldn't call it turbulent, really. It's just some kind of unsteady convection structure which arrange itself into these plumes that go upwards, and then some areas where it flows downwards. And of course, the convection is induced in the middle, but it's initiated by the instability in the electrolyte, but then it is induced in the top and bottom layer. And the induction is possible by two mechanisms, either by the shear or by just the heat transfer, so by forming some hot spots here and cold spots and so on. So they're both valid, but I think the second one is more important here. So this is the case when the layer of the electrolyte is thicker. We also have the convection, but this time it's organized differently. That's just the result of the aspect ratio of this unstable layer, the height to the width. If you look at the Nusselt number, which we calculate, we take the heat transfer at the top plate and bottom plate and divide them by the heat transfer we would have in a purely conducting flow. Then, and then we take the average of the two just to see if the thermal convection has any serious effect on the heat transfer. So this line here, we see no, it's not much anyway. And we also see that, of course, the heat transfer that goes through the upper plate is, in the case of the convection present, is higher than through the lower plate. And this is how the temperature profile, time average temperature profile changes as a result of the convection. So here I come to conclusions, which are rather simple, that even if you have the smallest cells, you are going to have this thermal convection caused by the heating of the electrolyte, Joule heating. At the same time, if you take these non-dimensional amplitudes of the flow and recalculate them into some dimensional quantities, then you'll see that the resulting flow is really, really weak. It's definitely exceptionally weak in the small cells of the size of the centimeters. If it's larger than that, if it's if somebody ever builds something like that on the scale of a meter, then probably these motions are going to be stronger. Yeah. And also we found that even though we included the MHD term in this, the typical magnetic field expected in this system, the effect of the magnetic field on the convection is going to be very small and can be ignored. So if you have any questions on that part, I'm ready to entertain them.
Are there any questions from the audience, or probably at the end of the presentation also?
All right, let's do it. Yeah, okay. So then I will go to the next one. Oh, that's the little kind of little off-road. So we just look, okay, but there was actually it is a very interesting topic, the thermal convection, which is induced not in the classical really binary scheme, not by the heated bottom plate, but internally. We found that it's quite a fascinating topic, which is by itself worth attention and not really that well understood. For example, unless you're really into that and you don't look into the special literature, you don't suspect that, unlike the really binary case, in this case, the bifurcation that results from the instability is not purely supercritical, meaning the linear stability analysis may present you with some critical or kind of with some critical really number, but in fact, the convection motion exists at the low ones, at the subcritical the values. So we apply the method of totally classical continuation, in which we go above the stability limit, find some solution, and then decrease the Rayleigh number in small increment and use what we have as initial conditions for the next simulations and so on until we obtain this convection solutions at lower Rayleigh number. And we did that just for a single layer, no metals, just a single uniform heated layer and domains of different size with stress-free top and bottom boundaries and uniform heating and the same physical properties as before. And we found, yes, indeed, it does exist. You must be very careful. You have to calculate that as a three-dimensional problem, otherwise you don't see the effect. And these subcritical solutions, they change very much with size of the domain, which is also expected. Also, it's very interesting theoretically, we have the structures like that, depending on the size. So for example, this one is at subcritical Rayleigh number, vertical velocity, but practically they have no value because this solution, they corresponds to exceptionally weak low amplitude flows. So they're not going to have an effect on the mixing, or they're not going to be to move interfaces or anything like that. So that's just to mention, if you're a student, it's kind of useful to look aside sometimes. So it's good to be focused on the problem you are doing, like in our case, it was the thermal convection, but it helps to think and to consider possibilities. If you read something and you find something unexpected, well, you may spend maybe a few months just doing something which is not directly on the topic, but still interesting. Okay, so now the next topic for me will be the metal pattern stability, which I will show in two different solutions. And this is the phenomenon which is known to exist to a community from this rather old history of trying to understand what happens in the aluminum reduction cells in the whole Joule smelters. Here the situation is similar, except that we now have 3 layers instead of 2. The key factor, however, remains that the electric conductivity of the 2 layers, top and bottom, is much higher than the electric conductivity of the electrolyte. And that brings immediately this scheme. Let's imagine we have this interface between the electrolyte and one metal layer. In this example, the top metal layer. It is distorted a little. It moves a little. So at some place, the thickness of the electrolyte is slightly smaller than in some other. It is exaggerated in the picture. If it is smaller, then it means that the local electric resistivity of the electrolyte layer is reduced here. So, and if you have an electric current, the total electric current which is imposed to flow through the cell, you will have more current in this place and in this place. But here is a highly conducting metals, so that means that this current will, at least partially, close in the liquid metal, and it will form some kind of a horizontal closing electric currents in the metals, right? Now, the idea is, what if you have an external magnetic field, not the one which is generated by this current, but something else from the outside, from the neighboring battery cells, for example. This magnetic field will interact with these metals in some way. There will be force, and it will move the fluid. What if some configurations of the magnetic field are such that the resulting Lorentz force moves the fluid in such a way that this initial deformation of the interface is enhanced? If it's possible, then it forms the positive, like enforcing feedback loop, and then the perturbations of the interface grow, and then we may have instability on our hands, in which we have kind of a sloshing motion of this liquid layers, with the interface deformation increasing, getting bigger and bigger until it gets so big that the upper interface touches the lower one, which results in short circuit and the, well, at least temporary cease of operation of the cell. So that's what we consider, not just us. We did it in a few steps. One was the simple mechanical analogy, which I'm not showing here. Another was the shallow water model, in which we assumed that the horizontal size of the cell is much bigger than the vertical size. And we only do it because we already had the model. Well, we only do it because aluminum reduction cell is like that. And we had developed models for the reduction cell, which could be, it was not very hard to adapt them to the battery. So it's not that we really see these shallow cells as something of special interest here. But anyway, so we consider this shallow system. And if it is shallow, then you can apply the approximations. And it's the approximations comes from the hydrology, where lakes are shallow. Other bodies of water are also shallow, the oceans, the kind of rivers, and they do apply the so-called Descendant shallow water approximation, which is not simply assuming that the flow is two-dimensional. It's rather more involved than that. You do the proper integration across the layers, and then you do approximate it by a two-dimensional system of equations, but with some additional terms. So we can see the system, we take, it exists in the presence of a uniform current, and we assume existence of a vertical magnetic field, because we know in advance that's going to be the dangerous one. And we neglect all the other effects, which are not interesting for us. I will skip the slides because it's just the modeling. It's basically, we do this integration over each layer, the top metal, bottom metal, and the electrolyte. And for each, we have the two-dimensional velocity field, and we can see that the perturbations of the interfaces here, A and B, top and bottom. And we get equations which look like this. And I don't think I missed anything here. So the momentum equation for two layers, metal, and for electrolyte, this is how the material derivative looks in this case, with the effect of the deformation of the interfaces here, and with the electromagnetic forces, which are here. And there are more equations. This is the mass conservation, because all these waves on the interfaces, they're all coupled by the conservation of mass and total. The base state is that there is no motion and constant electric current. And the Lorentz force is computed. Again, I would have to show you the paper to explain that, but basically we just consider exactly this scheme here. This scheme here, we just calculate what these electric currents would be. And we even try to include the viscosity effects, which is quite challenging if you go from 3D to 2D, because you lose a lot of information. So what we did, we included the normal viscous terms in the horizontal plane. And for the vertical plane, we used some kind of modeling by the linear friction at the interfaces. So the problem is solved in a very straightforward fashion by defining different discretization on a staggered grid. On a low resolution, you don't need much because it's a very smooth solutions. And if you do the non-dimensional analysis, then you see you have a couple of parameters which you may suspect as control parameters of the instability, one for each interface. For example, for the upper interface, that would be something like that. It would include the total electric current, total imposed magnetic field, horizontal sizes of the system, jump of density across the upper interface, and the thickness of the electrolyte layer and the upper metal layer, and the gravity acceleration. So that's the instability parameter that kind of estimates the balance between the Lorentz force, which is destabilizing the system, and the gravity force that is stabilizing it. Because again, here we have the system with a stable stratification. The electrolyte is heavier than the light metal. So any perturbation tends to come back just because of the gravity. And if this parameter is big enough, actually here is the dimensional parameters which we considered. You don't need much of external magnetic field really, but the cell we take here is rather large. You see it's 0.75 by 0.375 meter. So it's like a table size. We do have the instability. So the interface at a single point is growing, mean velocity in any of the free layers growing, the average values of the interface is growing, and we see these periodic fluctuations. This is because we have waves, and the waves are traveling around in the clockwise direction like this. So this specific case we are considering here is when the density of electrolyte is close to the density of the upper metal, but quite different from the density of the bottom heavy metal. So it means that we most likely will have the instability on the upper interface only. That's why we call it one interface, right? Because at the bottom interface, it cannot be caused due to the high density jump. And in this case, we have two waves, one much bigger at the upper interface, the second one kind of induced at the lower interface. And it's interesting that they are in opposite phases here. So blue is bottom, red is up. So they're kind of traveling around the cell in the opposite phases. It's as expected, actually, from the experience we have with the aluminum reduction cell. The horizontal aspect ratio affects this instability in a very, very, very big way. Here is an example. We have two aspect ratio, 3.0 and 3.3, and the critical values of the parameters are very different. So this one is much less stable than this one. And also, if instability occurs, the shape of the wave is very different. It happens because these instabilities can be viewed as a result of the resonance of the Fourier harmonics, which are of the waves of the Fourier harmonic waves, which are allowed by the horizontal shape. And these waves are change as soon as you change the shape, as soon as you change the aspect ratio. So the points of resonance also change. And this is an example of what we see in this case. So basically, depending on what we take as the horizontal aspect ratio, the growth rate of the perturbations varies quite dramatically. And for some aspect ratios, we have zero growth rate of up to this point, while for some, like for the square one, for example, the instability happens practically immediately. Now, here is an example. Then we have two interfaces with similar density jumps. They are, well, not the same, but of the same orders of magnitude. And here the situation is totally different. The instability occurs on both interfaces, and this time the deformation, the waves on the interfaces are not quite in phase, but sort of similar, right? So they kind of turn and slosh together. One slightly behind the other. And here we also have an effect. I think it's, no, this is for the single aspect ratio, but we changed the density of the electrolyte and see what happens here. So there is a lot more to that. It's so if you are interested, here is a reference which could be again looked into. And the last part I'm going to show is this the simulations which were performed by Linian Xiang, who has graduated last Friday. That was not his PhD work, that was his master's work, and it was published in 2019, which I don't think, yes, I know. Oh, I only showed the thesis really, but he published the paper in 2019. And he tried to do the same system, but for the real geometry in a cuboid cell using open foam. It is actually known that the open foam can be used for MHD simulations. And if you do it right, it can give you more or less reasonable results. It's not always easy. And the method is, of course, not the most effective one, but in the sense that it's kind of slow, but it works. So we took the typical parameter of the magnesium antimony cell. So the magnesium at the top, it's 10 centimeter by 10 centimeter by 10 centimeter, imposed vertical electric current and vertical magnetic field. Here is a system, structured non-uniform green. What we found, that's computationally, if you ever deal with anything like that, you will find that your biggest challenge is the sharp change of physical properties, most importantly in this case of electric conductivity at the interface. Because if you solve this problem using the finite volumes, and that's what we do here, the finite volumes are supposed to be conserving everything, including electric charges. The method, however, does use interpolation from the centers of the finite volume cells to the faces, to the sides. And if you don't do anything and just rely on the default option, which is usually the linear interpolation or some geometrically corrected version of such, then you're going to fail. And it's not straightforward to realize, but to properly approximate the fluxes of the quantities of the faces of the cell. In these cases, at least, well, in this case, around the location where the physical property changes, you have to use the harmonic interpolation rather than linear one. If you don't do that, the inaccuracy in representing the local electric resistance in the area of the interface will be way too high, and your electric currents will be just completely wrong. So, and also we found that the potential solution has to be solved to very, very, very low iteration error. Anyway, so he did that. He found the instability does indeed exists. He found how the electric current fluctuates and all that. And this is supposed to be a movie, but I don't think it works. But it's what the typical outcome of his simulations was, that the two interfaces and one of them is going around. And this is the electric current perturbations, which look messy, not like the nice and smooth ones which we got in the shallow water solution, but it's partially due to the fact that it is indeed 3D here, and partially due to the fact that despite all the efforts, some numerical error in the prediction of this electric current perturbations is still present in these simulations. So the conclusion of this work, well, I would have to look in the paper really, but well, the system does exist. The dynamic is complex, depends on the density difference. And the most importantly, you can simulate it using OpenFOAM. So that's the end of my presentation.
Excellent, great, thank you very much. So we have enough time for questions from the audience, so colleagues, feel free to ask. Yes, go ahead, Professor Ramos, please.
Very interesting, Professor Zikanov, thank you very much. I was wondering, in the first part of your talk, when you were considering the natural convection without the electromagnetic effects, you, I don't know if you can include in your analysis the fact that the cells grow and diminish as the process goes. So the aspect ratio of the system would be changing, and this might be a major effect when the aspect ratio goes from a little bit below 1 to a little bit above 1, because the natural convection pattern would change. And so I don't know if this is important, but if you look at it from the purely hydrodynamic point of view, it might make a big change in the flow and Nusselt number and everything, because of the different convective pattern.
The layer of electrolyte isn't going to change in thickness, because, well, if we believe this heme, then the ions just pass through the electrolyte and they land at the bottom, or they go to the top layer. The electrolyte line is simply shifting up and down. It's not really changing much in the thickness.
That's right.
In that sense, I don't think it would have an effect. The other variations, it would, but we consider that charging, discharging, that's the process that happens on the time scale of what? Hours, maybe? Tens of minutes for sure, hours probably. Depends on the size of the cell, of course. And the processes we consider here have the typical time scale of seconds or tens of seconds. So in this sense, we can say, yes, there will be certain changes in the process of functioning of the cell, but they're going to happen on a much larger time scale. So we just fix a point and look at it. But I do agree that the situation would strongly depend on the stage of the cell operation.
Okay, thank you very much.
All right, I have a question in the chat.
Exactly, there is a question in the chat. So could you please says, hello, thanks to Professor Zikanov for his excellent talk. How is the electrolyte potential distribution across all involved phases taken into account in the modeling? How could you determine the ohmic effects and mass transfer polarization to infer the effect to calculate electric fields and hydrodynamic phenomena?
Well, yeah, that's the answer is we do make a lot of approximations, like the mass transfer polarization. They don't really take it directly. We just assume, okay, there is an electric current, and the electric current implies electric potential, and then we just do the let me open this. We just write the equations in the magnetohydrodynamic approximation, which does miss quite a few of electrodynamic, electrochemical effects for sure. So basically what we do, we just take the Ohm's law. The potential is supposed to be a three-dimensional field distributed over all three zones with, of course, with different electric conductivities and the interfaces on them. And then we assume instantaneous electric neutrality of the liquid. So we have this here. And that's it. And then we have the Lorentz force. That's all. That's the limit of the model, but the model is three-dimensional, and the distribution of electric potential is recalculated at every time step based on this model. Does this answer the question?
Yeah, hopefully. Yeah, I'm sure. So he didn't reply. It seems that Fernando Rivera is facing issues with his microphone. So. Okay, any more questions from the audience? Yeah, Sergio Cuevas, Professor Cuevas, please go ahead.
Hi, Oleg, thank you very much for this nice talk. I was wondering about the first part part of your talk, at the end, you mentioned that the formation of the interface is rather slight and that it could be more important when the layer of the thickness of the layer of electrolyte is thicker. But I was wondering, even if it is small, this deformation, in the case when you could have an external magnetic field, could this deformation trigger the other instability?
Oh, yes, yes,
Yeah.
yeah.
So because these problems are, I mean, the effects are coupled, okay?
Yeah.
Yeah.
Well, I totally agree. Of course, yes, one can trigger the other. Yeah, and but we know that there are a lot of other things, right? There is this electron vortex flow. There is the solitary convection. There is a Marangoni, that and this. I mean, they all coupled and they all interact and trigger each other. Yes, it's true. I agree.
Okay, and but for that to happen, you need an external magnetic field, not just induced magnetic field, right?
For the rolling pattern stability,
Yeah.
yes, it can be proven that it cannot be generated by self-induced magnetic field. No, it's not.
Yeah. Okay. Okay. Thank you very much, Oleg.
Oh, yeah. Fernando Rivera just wrote on the chat. He thank you, Professor Zikanov, for the answer to the question. Yeah. So I also have. Yeah, I also have one question regarding the first part of your presentation. It seems from your results that when you increase the thickness of the layer for the cylindrical configurations, the velocity magnitudes on the planes that you reported decreases. I mean, it seems strange to me because you are increasing the volumetric heating, right?
Sorry, if you increase the thickness of the layer
of the electrolyte layer, it seems that the velocity magnitude decreases
at the same radius. Well, what I show is a non-dimensional velocity.
Oh, yeah.
I would have to recalculate to see what they're really doing. I would say yes, they must be increasing probably in dimensional units for the simple. Okay. And that's, yeah, yes.
Okay, and also in the simulation regarding the cube configuration, the cuboid, you have an external magnetic field in the opposite direction to the current, right?
No, it doesn't matter in this case. It can be upward or downward. So far it is vertical, it doesn't change anything.
Okay, so it doesn't matter if they are in the same direction.
No, it's not.
No, okay. Okay. Have you ever tried to study at the other, I mean, at the beginning you mentioned that basically you are studying the charging configuration for the batteries. What about, so that means that for the discharging processes, same behavior will be expected?
For the discharge, yes, it's yes, that's a good one. For thermal convection, it's probably wouldn't change anything, obviously, since we said that electromagnetic effects are negligible and the Joule dissipation would be the same. For the rolling pad, I think the direction of these traveling waves would be reversed. I think we even tried that, and it is indeed reverse. So it's not clockwise, but it's counterclockwise. That's all.
Okay, great. Thank you. Any more questions from the audience? Maybe feel free to also write on the chat the questions. Well, it seems that there are no more questions. So, well, yeah, it seems that there are no more questions. So this is it. Thank you very much again for your time, for this very nice presentation.
Thank you. It was good to be.
Yeah. Great. Thank you. Have a nice day.
Nice.
Thank you everyone for joining us today.
Okay.
Bye-bye.